So now it's very loud. Okay.
It's too loud.
That's too loud, yeah. So we make it in such a way, just the balance. I put it on my belly. How is that?
Here we're trying to trade.
And we take the turn down, so we make the sound larger and the light dimmer. Ooh, this is blue. Does that work better? All right. Good. So now we have that. And this is atomic hydrogen, seems to work fine. There will be a theme there that atomic hydrogen seems to work okay. There was another measurement we did. There's another instrument we have on NSTX at Princeton. It's just a grating spectrometer with, to measuring EUV lines. And we looked at this into the plasma. And originally, we were actually, this is astrophysics, so we do iron. And this is the M-shell spectrum of iron at around, here's the 171 angstrom line. And that was the purpose, to measure it. There was a resurgence of iron fell into the plasma again. Here what happens is you can see actually a little bit of a curvature. What it is, this is wavelength, this is time, so it's time dependent, and it just moves from here in time. And actually somewhere around here is where a neutral beam again heats the plasma, it gets so hot, and iron basically, the M shell burns out. We don't see it. But then some new material fell in, and we looked at it, and lo and behold, we found new lines. And we were all this excited because here's the iron 171 angstrom line of iron 9. For those of you who know, these are all higher charge states. It was already pretty hot, that's why this is going away. But if you look at it, at the black spectrum is typical, and you can kind of see this being just iron, M-shell iron. But then there were a few lines like in the red spectrum here. This is enhanced by a factor of 2. See, most of the red lines get weaker, but here it got bigger. There's one line that's completely new. That's this one at about 188 angstroms, roughly. And there should be one more, and I started. Oh, here's another new one. So you can actually see it. And so initially we thought this is iron, but there are no iron lines. As we went through, it's carbon. So it comes from carbon, right in the spectrum. But then you do collisional excitation. And it turns out that in the spectrum you see helium, carbon-5, helium-like carbon in fourth order. And Lyman alpha, I'll show you later, fifth order and all of that stuff. So you can actually, once you believe the calibration of your instrument, predict with a collisional excitation model, relative to these lines, how big collisional excited carbon should be. Here they are. See those little ones? Well, the point is they're too small. So you go through collisional excitation, doesn't work, and then of course this is a charge exchange meeting, so you know what the answer is. It must be charge exchange. And by the way, here's the hydrogenic. There's Lyman alpha in fifth order. Here's the corresponding directly excited line of hydrogenic carbon. And now here's the same spectrum, a little bit different wavelength scale, with most lines labeled that come from fourth order and fifth order, carbon 5, carbon 6. Here's carbon 6 again in fifth. Oops, this should be sixth order. This is when you cut and paste. See, they're all in fifth order, but here it's correct. So fourth and fifth and sixth. And this is the one hydrogenic line in charge exchange. It fits. Actually, surprisingly well. And these are the lines from helium-like carbon. And again, it's with hydrogen. But it does not, it's not from the neutral beam. And I don't think I have, this is at 100 eV energy dependence. And the next one I show you, it looks almost the same. See if I flip back and forth. It makes a few lines different. That's at 1 kilovolt. We can bracket it, but it makes a difference. If you go to 10 kilovolt, 100 kilovolt, it doesn't work anymore. You go to 10 EV or 1 EV, certainly doesn't work. That goes back to the energy dependence of these spectra. So we now know there are lines from carbon in the M-shell ion spectrum. And it kind of works. But that's hydrogen. But most other things that don't work is when you have multi-electron capture. With atomic hydrogen, you can't do it. It's just one electron to capture. But most of them is double capture, triple capture, and larger. And this is multi-electron capture. And this here is argon-16 plus spectrum, but it's produced by hydrogenic argon interacting with neutral argon. And like you heard before, Tanuma-san was talking about making the energy higher. Ours is thermal energies. And we have an ion temperature of about 200, 300 or so EV, 400 EV. So if you take a 400 EV ion, and like argon have about 40 nucleons, so it's 10 EV per nucleon. That's what that number comes from. And this is a calorimeter spectrum. And it's actually relatively old data, because you will see this is with the old microcalorimeter. Its energy resolution was about 10 eV, but we never published these data because we haven't had funding for about as long as the spectrum is old. So we haven't really published these anymore, because we've had a little bit of funding from the Goddard group gets money to develop the calorimeters. So right now, actually, Maurice Leutenegger and his student Gabriel Bettencourt are in Livermore trying to do, again, a little bit of charge exchange. But we at Livermore ourselves don't have any funding. So we haven't really published any of this. But again, here's the resonance line, the two intercombination lines, and the forbidden line. You recognize them. And then you can take some of the CTMC calculations. And this is a calculation for 10 eV per AMU. And you will find this here matches okay. This is always where I normalize to. This one is a bit higher than what's predicted. And so you do this as a function of energy. And then you find this one actually seems to be relatively good. And this is the one at 100. So you can see, like the intercombination lines, is a dependence on the interaction energy. And the best one you can kind of find is maybe for this one. They seem to match the best. But then we had, this is though for argon. With argon, we did also, and the predictions though for argon with atomic hydrogen. There is no double capture in this spectrum, the predicted one. So we did another measurement of argon with H2. And notice, by the way, the resolution improved. It's because it's a new version of the calorimeter, which we installed in 2007. The resolution is better, but the spectral intensity has changed. You notice that. Look how big the X and Y are. Oops, at the intercombination lines, and how much it dropped down, for example. So it depends on the interaction gas. And here, the best fit may be this temperature. Well, so in the other one, maybe 100 eV, this one is only 1 eV. It's probably neither. And the main thing is, of course, there is a possibility of multiple capture. And you can see this even more when you look, this is what I showed you before, when you look at the Rydberg series. This is the 3 to 1, the 4 to 1, 5, 6, 7, 8, 9, 10, 11 in here. It's not that great statistics, but they're there. And the predictions are here. This line is much stronger than predicted. And then it has an excess here, which we don't see. But of course, we have to include multi-electron capture. And in the meantime, since the time we took those data, multi-electron capture has now been put into the models. And there was another spectrum like this just published very recently from an ECR source in France at Ganil called Aribe, and Aribe, probably the silent E. And that's their spectrum. This is the resonance line, the intercombination line. The forbidden line is very weak. We've heard that before because it's a moving beam, and it usually, like you had mentioned, you may need a laboratory that's 1 kilometer long, or maybe longer if you could. They still see a little bit of it, and that's because they look at some angle, but they have a little bit, and they even see lithium-like lines, but that's, they say this is due again to metastables, forming the metastable level here, recombining, making lithium-like. So by a few percent in their beam, because their beam has these metastables. So that's this, and then they have that Rydberg series, 3 to 1, 4 to 1, 5, 6, 7, 8, and so forth, and here it's blown up. And so they used the crystal spectrometer and got that, have nice statistics, a really beautiful spectrum. And then it was modeled, and here is the spectrum. This is, I shouldn't say spectrum now. Here's the answers in black. It's hard to see because some of the theory now is on top. But here you can see some of the black dots and connected for the 2-to-1 transition, 3-to-1, 4-to-1, 5, 6, 7, 8, 9, 10. This is a log scale. Everything is more forgiving when you show it on a log scale. But this is when you do single electron capture and make your model. And that's kind of what I showed you before. It was single electron capture, so it doesn't quite fit. Especially a lot of this here, the 3-to-1, 4, 5, 6, get under-predicted. And to bring that up, the theorists, in this case, Salehzadeh and Kirchner, 2 years ago, wrote a paper. The data was from 2012. It was shown, we never published that, like I said. So, 2012 they published it, which was also nice. And then they did a theory and showed that if you put multi-electron capture in, mostly double, then you can match quite well. It looks actually very nice. So 2-electron capture is very much necessary when you have such a target of argon-16 plus produced. I don't think I say what it is. It's argon-16 plus produced by hydrogenic argon with argon, just like what I showed you before from our machine. And so here they put the theory in, but there's still some discrepancies here. So no matter how much double capture you don't have that enhancement at the high end that you see experimentally. And don't forget that's a log scale. So this here, this distance is like a factor of 3 off. It's not minor. And then when you do all of that, unfortunately you get capture into n equals 10, which you don't see. You always have a little bit of these problems. And there's one other thing that's not quite correct. Notice when they added all of that together, they no longer normalized to 1. So you see this beautiful fit? Well, you know, I'm kind of nasty. I just basically used my Adobe, Illustrator. I took the curve and normalized it where it should be, because experimental, this is not an absolute scale. And I normalized it again to 1. Then the agreement is not quite as good. Though this discrepancy is not as bad. Okay. So this is still an open question. So even data like that, even when you put double capture in, you get much better agreement. I mean, these are huge factors of 4 here, right? But it's not perfect yet. And I want to show you something that Brad actually published. Even this was done at Livermore again with the microcalorimeter. This is hydrogenic iron capturing from H2 and capturing from helium. And we only had predictions not for H2, but we only had it for helium. And the predicted values, the N capture, just where you should capture into, were predicted to be 8 and 9. And that is at 1 keV per AMU, and at 9 and 10 at 100 EV. I'm sorry, at 100 milli EV. So this brackets things quite a lot. I told you it could be 10 EV per AMU. So we have the 2 limits just to show you there is a slight dependence. But we measure it at 11 and 12. If you take this trend, you know, you have to go to near absolute 0 to maybe get there. Yeah. And you cannot just use multi-electron capture to make any level different. It doesn't bring that, it doesn't work. But so there are little problems, and that just means it's not completely solved. And there's another issue, and that is one where this is a measurement at the Berlin EBIT of argon, 18 plus with argon. So this is based not helium-like anymore, so this is mostly hydrogenic argon emission, so it's Lyman alpha that you would see here, beta, and then the high end limit is here. And that's when you look inside the trap, and that's when you do exactly the same measurement and you go outside the trap. And they don't look the same. So there's something going on, most likely associated with magnetic field, that you may have inside the trap that you would not have here. So that's still a caveat. But I'd like to introduce this spectrum because it's going to be fitted with in a new paper now from last year, very recent, with multi-electron capture. So let me go on. But this here, this very high limit, so this was what we termed at that time the hardness ratio, because when you had Chandra, you had only a CCD type resolution. You could only, well, it's about 100 eV, and if you look at something like oxygen, you can't see any real individual lines, but you could break it apart between what's in the n equals 2 to 1 versus anything higher, 3 to 1, 4 to 1, so forth. We just called these X-rays, the harder X-rays relative to the 2 to 1, the hardness ratio. And here's a plot of what was done. So when we measured it inside the trap, we got a ratio that was about 1. This was our measurement. This is what I just showed you from the Berlin group, because this is all for argon, all for hydrogenic, making hydrogenic from Bayer. But they then took it outside the machine and did it as a function of collision energy. So these were all plotted around 10 or 7 eV per AMU. And then they made a beam out of it, so you could vary the energy. And you show it as a function over of energy over several decades. And there's also a point from NIST EBIT, also outside the machine, where the EBIT is just used like an ECR source, just a source of ions. They seem to all fit here, and these were the predictions at the time. This is, again, classical trajectory Monte Carlo calculations, and they become more or less statistical at the high end, high energy limit, and there it is. It was very simple. So the Berlin group basically said, well, we find the same value as Livermore, but when we go look outside the trap and do a beam, we have this ratio. Okay, and now Otranto et al. Just last year, and Olsen, I think they were Sebastian and Ron Olsen, wrote a paper where they now fitted the data outside. They could, with a multi-capture model, and instead of having this kind of trend, that's the trend they get. Looks very good, doesn't seem to agree here. This is still a puzzle, it's not clear what it is. So let me show you. So this looks very nice, and this is the fit of the data from the Berlin group, and I just want to point out what's in here. So first of all, normally you take single electron capture, and that's the curve here. Now, before it wasn't so bad because you scale this back up, right? You always, this is an arbitrary scale, so you bring that up, but it's not as perfect. So then you add double capture, followed by autoionization. And that effectively makes it, again, single capture, but it shifts everything down. And that's that orange trace, that's this piece here. It basically adds some, mostly here, not at the higher energy limit, but always further down, because you lose energy when you autonize something. You always lose energy.
Peter, could you tell about the ratio of cross-section, for example, double electron capture?
I will in a moment.
To single, because
I will in a moment.
Important to understand
Right.
what's the fraction of this here.
Yeah, but you now have these additional ones, and then you have a few cases where you actually just decay by radiation. And that means when you have bare argon, with argon, it doesn't just produce hydrogen-like, it produces helium-like. And here is on the shoulder, that was helium-like, and this is what they have. And then they put the total. And that's how that previous fit came about, this kind of prediction just for the hardness ratio. So they just looked on how much is in here versus what's there. And that's multi-electron capture. But, so now here, I look at that slide. It basically says, we looked at this again, the role of multi-electron capture. And I'll show you the ratios in a moment. So give me a few more seconds. So this is what we looked. We actually used the instrument. So I'm not showing that data from Livermore, but from Reno. And that was, we used an ECR source at Reno and a triple coincident measurement, where you actually look the X-ray produced, but also you look at the target, its recoil, and you look at how much charge it lost, or how much it gained, sorry, in this case, charge, how many electrons it lost. And then you look at the ion that originally came, called the projectile, and see how many electrons it picked up. And sometimes they don't match, right? The donor lost 2, and the other one picks up 1. That means it actually picked up 2 and ordinary ionized together. Now you have triple coincidence. Now you can actually make all these ratios. And what we find is, of course, that multi-electron capture is about half of all the captures. And we found that even when we now limit it to single electron capture, because we now have all these coincidences, you just throw those out that were multi-electron capture. And you only look at spectra from single electron capture. You still can't quite fit them. And if you then add double capture, and this is the new thing that we just had, it actually decays in ways that are not yet in the multi-electron capture models. So I just showed you those models, and what we're saying, those models are not yet complete at all. They're better, so I showed you, but they're not complete. This is our setup. This is kind of the experimentalist's equation, so I won't talk too much about it because I haven't seen too many equations on this meeting. So I don't want to bore you too much, but here's the gas jet, here's the X-ray detector. This looks at the beam comes in here. We look always at bare neon, it comes in, and we look here whether it is still bare, hydrogenic, or helium-like, or less. And over here, the gas drifts over into another detector that looks at the donor gas, whether it gained a charge or lost electrons, etc. And here is a picture of it. Beam comes here, so I'll skip this. Okay, this is our first set of data, was just to look at how much is multi-capture, how much is not. But let me show you what this picture here does. This here tells you of any of these things on how much. Here is a projection of this onto here. This says these here are argon 1+. This is now, I should first say, this is bare neon. Everything here is bare neon when it comes. In this case, it interacts with argon, so argon is neutral. In this case, argon lost 1 charge, so it's argon plus. This is argon 2+. This is argon 3+, 4, and there may be a hint of 5+. So sometimes the neon picks up 5 electrons. It's very rare. But 4, 3, 2, or 1. That's single electron capture, pure single electron. This is pure double. Then you look at here in this column. These here are those that are neon 10+ going to 9+. And these here are neon 10+ going to 8+. So that means up here, and this here is just overflow. So this is real data, not background subtracted yet. But you have neon 10+ coming in, it picks 1 electron up, becomes 9+. Here, 10+ comes in, picks up 2 electrons, and it either becomes 9+ by autoionizing again, or it becomes 8+ by never losing it. And it has to just decay. And then you go down here, these are the corresponding, here, it's the corresponding X-ray spectrum that we have. So let's look at one of the X-ray spectra. So this is basically everything. So this is the alpha emission, the 2 to 1, and this is 3 to 1 and higher. And then, of course, we just make a gate out of those, whatever, about 40 or 50 million counts, because by the time you do triple coincidence, there isn't that much left because of the solid angle. And this is pure single electron capture out of the fraction. And in this case, for neon with, this is, I'm sorry, I switched you here from neon to neon. In this case, it's about 58%. 42% was double capture or more. But this is pure electron capture. And you notice it shifts a little bit higher over here and things like that. This is also, by the way, done with a windowless detector. But, you know, there's a slight, even windowless detector, because there have to be electrodes. It has a tiny, a few hundred microns of copper on it. So you have to take that into account. It makes about 2 or 3% here. It's kind of negligible, but we do take that into. In that case, we did model it. So just to make sure. Okay, and then of course, this is the multi-electron capture distribution, and now you can see the multi-electron capture surely shifted over because it loses energy, especially when it automatizes. Okay, so we have that fraction. So now, what if we only consider single electron capture? You can do more cuts to this. So we're now going to look only at the red one, and now you want to determine, because we have energy of the projectile, and the projectile energy when it recoils tells you whether you captured in n equals 4, 5, 6, or 3. You get that information. It's called the Q value. So this here was the total spectrum. These are the experimental data that I just showed you. This spectrum is this red one. And then this is the best model from CTMC. And I don't know, Phil, I think your name was on the paper, so he's responsible.
CTMC.
And also, where's David? Oh, he left.
Yeah.
Darn. He told me he had to go to another meeting this afternoon. But he's really responsible since he's not here. But you notice...
Why he left, now it's clear.
Yeah, it's very clear now. But you see, there's an excess here and it's less here because the sum, the area is preserved in this case. We didn't just scale randomly. The area is preserved. And you notice that hardness ratio is just too small because this is very weak here. But we can do better than that. This is just the total signal. Here it is capture into n equals 4. This is the signal for capture into n equals 4. These are the predictions from CTMC. This is for capture in n equals 5. It's better. And this is for n equals 6. And more or less those three make up that. There is no capture really in n equals 7. It's minuscule. We can't see it. And certainly none into n equals 3. You can actually see how much of it because these numbers are on a real scale. So most of it is into n equals 5 in this case. This is single capture only. You cannot say this is due to the bad fit is because of multi-electron capture. This is what you get when you do triple coincidence. I mean, to me it was beautiful. Rami set up this experiment, and I was just thrilled when I saw this. And here, I think that the last one was on helium with neon. I switch every now and then. I always, you have to read with me. This is neon 10 plus with helium. Here is again neon 10 plus with neon. And I also have argon. I won't show it. And again, that's the total sum. And here are the individual n equals 4, 5, and 6. It's slightly better here. And here it's underproduced. First time they changed around, actually. 6. It's very important. Now I told you, this is selected to be single capture. I just say this, so theory still didn't quite work. And the interesting thing is, the people who gave some of the predictions I showed you earlier, I think it was, oops, doesn't show up. Which one is this from the, I think, yeah. There's a new paper, just last year, where they used, instead of CTMC, they used, I spelled it out here, two-center atomic orbital close coupling method. I really don't know what it means, and I missed your talk yesterday. I'm sure you explained it all. It's a different way to look at things, and they said, well, our fit is basically the same as CTMC, more or less the same. They actually say that. And therefore, this is clear evidence, these deviations, that there must be multi-capture. Didn't quite get the point. This is why I harp on this so much. Please, there is no multi-capture. We selected it all away. Unless we made a mistake. You know, Maxwell Demon somehow allowed it. But this happens.
Peter, but nevertheless it's evidence that you have something on the top. Yeah, maybe it's cascading from highest capture which you can control. I don't know. Because it's
there could not be any high capture.
Yeah, but you have something above, yeah, this theory. If you mentioned that both calculations, they are very different, they agree,
yeah.
I believe in theory in this case. I trust you, certainly. Yeah.
Well, if you trust me and believe in theory, there's a contradiction.
Yeah, I try to resolve it here.
Okay, well, it's the particle, it's like duality, wave-particle duality. There is a
I
way
thought about this. Is it possible that you have just a recombination processes, electronic capture, for some reason?
Shouldn't be. This is not a trap anymore. This is a cross-beam experiment.
Cross-beam.
It's cross-beam.
Yeah.
Sorry.
Yeah.
Causing headaches. So I'm almost done. But we also opened the question and answer session already. This is now where we select only double capture. No more single capture. This is where we deliberately decided only double capture. And this is for helium target, neon target, and argon target. This is double capture followed by autoionization. That's what the A stands for. So we know that the neon went to 9+. And this is here where neon went to 8+. It was true double capture. So 2 electrons came and they stayed. And we can select them. And this here is the Q value down here is what's plotted on these 2D images. It's just projected down here. So what that means, this is, let's do this one. This is neon on neon. This blue peak corresponds to the single electron, the double capture, but you end up with 1 electron capturing into a level 4 and 5 because you captured 2 now. This is the energy. 1 electron goes to 4, the other one to 5. This is where 4 and 6 would be, that energy, and this is 5 and 5. Over here would be 3 and infinity. It's hard to resolve these. But this peak is 4 and 4. So that's very distinct from 4 and 5. For double capture, true double capture, you see most of them are 4 and 4. It's the red one. The true double capture is a small fraction of this. In helium, it's about 30%. In argon, it's about 25%. So it depends on what happens. Because this, the red one is the TDC, the blue one is from up here, the ADC. So now I'm going to just focus on this dashed area where you get a peak. So now you know where it came from. I'm going to actually focus on this one, on neon, in my next slide. It's going to look at what happens to the 4 and 4 capture. And I'm going to look, I think the first one, I used the 4 and 4 of helium because it's such a bright signal. You can see right here. And if you know it's in levels, the 2 electrons where they go. And so I'm going to take this, and it's in 4 and 4. One other thing I can tell you. There is a way, we know in some sense from a little bit, from additional information, there's somewhere here also, it's called beta milliradians up there. It's kind of the projectile deflection also tells you a little bit more on how it's captured. So this here is actually 4 and 4, even though energy-wise it coincides with 3 and infinity, which means high end. Okay, so here's the spectrum. So let's talk you through first the first one. This is where 2 electrons were captured, 1 got thrown out. To throw out 1 when you're in 4, you have to give it energy, so it goes from 4 down to 3. So it cannot be higher. There's nothing higher. See. This peak is 3 to 1. Because there's only 1 electron left, this is purely hydrogenic. This is Lyman beta here, this is Lyman alpha. There's not much else to it. But now you have 2 electrons that are there, and they start at 4 and 4, and they do not decay by throwing an electron out. These, in the case of helium, almost invariably will go down by X-ray emission. I can tell you the fraction of it. You can see the fits here. There is, this is the, here, K gamma. This is where you have n equals 4 with a n equals 4 spectator. That happens to be this fit here. And then, according to the fits, about 20%. That's when one of the 4 electrons goes down while having a 4 spectator. There's another one here where it's the beta line, where it goes down 3 with a spectator. We don't know, we can't resolve in that spectrum at all where it comes, so we just call it n prime. This here is the 2 to 1. Don't forget, this is helium right now. There are 2 electrons. This is the typical K alpha, helium alpha, whatever you want to call it here. This peak is the strongest one, but it is with a high-end spectator. It's usually 4. And then there's a little bit where it is, one is already in 1s and the other one comes down. By that time, why is it so small? It should be more or less the sum of all of this. It has to end up like that. Don't forget, this is a moving target, a moving beam, and this takes time, and if you only have 4 nanoseconds during which you can see everything, and then it's outside of your region of interest. So it takes time for all of this to happen. So the first thing you will see is the direct excitation, direct decay. So the points I want to make here is a large fraction of the double capture is true double capture. Large fraction is between about 15% to about 34% of the cases we studied. Surprisingly large fraction decays by X-ray emission. And it's what that means, and not by autoionization. And when it does that, this here contradicts those models that were implicitly in there, because when you have people do double multi-electron capture modeling, they say if the electrons are in the same shell, 4 and 4, they're autoionized. And they don't, in this case, I guess. And now I show you the other case of neon. It's truly not going to be my second last slide. This is for neon. Neon with neon, sorry, because it's always neon. So neon and neon. Oops, neon and neon. But the same will happen for argon. But this is for neon with neon. This is again Lyman alpha, Lyman beta. We know what happens. But here, notice there is no K gamma. But it is double capture. And it starts with 4 and 4 because that's how we selected it. Why is there no n equals 4 decay? This is weird, right? From what I just told you. And you look puzzled, and you should be. And what happens is the 4 decays to 3 by promoting the other electron to about n equals 9 and higher. Not autoionizing, we would detect that. But it has to be in a high-end level. And that's what we call, and other people, auto transfer. It decays down to n equals 3, and it somehow promotes the other one to a level like 9, 10, or something like that. But that is very important. It didn't go away. It still is there. It actually did not, it still has all its potential energy that it can de-excite with. That's very important. And this is the fit that we have. So we know we started with 4 and 4, but that's why we have these 3, n, where it has redistributed itself. So it didn't tolerate 2 electrons in the same level, but it didn't autoionize, it auto-transferred. And that's again not something in the multi-electron capture models. And when you put those together, you know, there's some missing parts. And we try to show what the missing parts are. And I'm running out of time, so I'm just, I'm summarizing what I said. Multi-electron capture represents roughly half, when you go for different cases, of all captures. If we rule out multi-electron captures, focus on single electron captures, you still can't fit satisfactorily. I hope I convinced you a little bit of that. And so don't always believe, oh, if you just put more stuff in, it'll fit. Yes, but it has to be scientifically sound. New models that include the multi-electron capture do not have all the decay paths. They're not all in there. And of course, oops, this is misspelled, but nevertheless, between 25 up to 50% of all double capture could be true double capture. And this is what I mentioned, what's not in the current models. Both electrons, even though in the same shell, can decay by X-ray emission, or they can, when they're there, can decay by auto-transfer, where one drops down and the other one gets promoted to a kind of a Rydberg level. And this is my summary. I think a large progress has been made, and there's still significant issues to address. I think I convinced you this. Everything so far has been on K-shell, and we hope someday we can study L-shell. Here, by the way, is a sulfur spectrum with direct excitation. This is what it looks like with charge exchange. You know, you can make sense out of that. We wrote a paper because it was for Jupiter. It's when we still had funding from that. And finally, because this is in memory of Alex Dalbrano, I'll just show you a few pictures. The formal talk is over, but when I heard that he passed away, Jan, who was also at that meeting, dug up some pictures. That's why he's not in the pictures, because he took many of these photos. There's Alex, and this is on the walk. This was in Africa. You probably hadn't seen this because probably nobody was in Africa at that time from this group. This is Hui Chen, who's a co-worker at Livermore. Many of you know her. So that's where we were. That's our lecture hall. And you see, this is Alex lecturing, and there's quite an attentive audience. And surprisingly enough, when other people were, Alex at his age still paid a lot of attention. That's not true for everybody. And notice he's also a quick eater. And that was at the dinner, and that's the final picture. Thank you.